recording also just start. Okay. So let's commence with the proper part of the course today. That is, the last 2 days we have been talking about Bose-Einstein condensation, which was sort of a warm-up towards what we need to do. And also, of course, it's very important because in a sense, you will see that both of the two phenomena that we are going to talk about, superfluidity and superconductivity, are in a way connected to Bose-Einstein condensation, if not directly, but at least indirectly. Today I'm going to talk about superfluids, and so we will begin with a description of what superfluids are. And today's talk will be primarily sort of an introduction to superfluids and a bit about the history. The history is also pretty fascinating. But while I talk about the history of the discovery of various superfluid phenomena, I'm going to describe some experimental things that told us that these phenomena occur. And these experiments are, of course, very important as far as the rest of the physics is concerned. Now, fluids. Superfluids are, of course, special cases of that. But what are fluids? What does the word fluid mean? Anybody? What is a fluid? Yes? Any one of you, tell me what a fluid is. After all, if we are going to talk about superfluids, we had better understand fluids first, right? So what is a fluid? Any one of you? If I don't get an answer, I will be very worried that I'm not really connected.
State of solid having viscosity.
State of solid having viscosity. Are you sure about the wording? First of all, I'm not asking you to contrast it with the superfluid at this stage. I'm just saying, what does the word fluid mean? When you say something is a fluid, what do you mean by that? And solids definitely are not fluids, by the way. Those are the things which we sort of rule out at the very beginning. So, well, in daily life, we know of two kinds of fluids, which are liquids and gases. But the word fluid actually means something which flows, right? That's where the word fluid comes from. Anything which can flow is a fluid. And in that sense, solid, something which is apparently solid at least, glass, for example, is really a fluid with a very, very high viscosity. If you go to a very, very old church, you will see that the glass in the church window is thicker at the bottom than at the top. That's because over the centuries, the glass has flowed down under gravity. But typically, things like glass are not what we call fluids in our everyday experience, because in our everyday experience, we talk of fluids as something which flows. Liquids flow, so do gases. But one thing which all common fluids have in common is that when they flow, they experience friction. But we don't call that friction. What we call that is exactly what was said a while ago. We call liquid friction viscosity. So when layers of fluid move with respect to each other, there is a force between the layers. The faster layer, suppose I have a layer of fluid which is moving fast, another layer which is moving slow. The faster layer will exert a force in this direction, trying on the slower fluid, trying to make it speed up. And the slower fluid will, of course, apply an equal or opposite force, action and reaction, basically, on the faster layer, trying to make that slow down. So ultimately, just like friction, where the job of friction is to ensure that there, at least to try to reduce relative speed between two surfaces. That's exactly what viscosity does. If you have fluid whose parts are moving with respect to each other, they try the different parts experience the frictional force on the other parts, which tend to try to equilibrate the velocities. That is, if something is moving faster, it tries to make it slow down. If something is moving slower, it tries to make it move fast. Right? So now in your labs, at least till date, you must have done experiments involving viscosity. What kind of experiments have you done? Yes?
Determining the terminal velocity.
Yeah, so that was called something like a Stokes law experiment, right?
Yes.
Which where what you did was have a tube of fluid in which you dropped a small ball, right? And that small metal ball moved through this thick fluid, typically castor oil or glycerin or whatever, and slows down and reaches terminal velocity. But where exactly does viscosity come in this? Because after all, viscosity is friction between layers of fluids which are moving with respect to each other. Here, in this experiment at least, what you see is a ball which is moving through liquid, right? So why is there viscosity? Which is, remember, a liquid to liquid phenomenon. Yes?
There is a friction between the layers of the liquid and also between the ball and the liquid.
Good. Basically, what happens is when the ball falls to the liquid, it carries with it a layer of the fluid very close to it. That gets stuck to the ball more or less. So this layer of fluid is moving with respect to the rest of the fluid, and so it makes the next layer sort of feel a force. In fact, the next layer, which is moving slowly compared to this inner layer, will feel a force which will try to speed it up, and the inner layer will feel a force which will try to slow it down. And that this layer, of course, drags the next layer and next layer and so on. So basically, a falling body through a fluid experiences a frictional damping, which is basically due to the fact that the liquid layer which it is carrying along with it experiences a viscous drag. Okay, fine. So that's where Stokes' law comes in terms of viscosity. But one question, did you ever try to measure the viscosity of water using this method? You did this Stokes' law experiment in class, right? I hope that you were in the labs before the pandemic hit, right? Which year did you enter BSc? Or that was before the pandemic, right? Or after? My recent geography and history has gone completely screwed up. Yes, which year did you people enter BSc?
So 2018.
18, right? So you at least had 2 years or 1.5 years at least of labs. So you must have done the Stokes law experiment in the lab, right? Yes or no?
Yes.
And the question is, the liquid that you use there must have been either glycerin or castor oil. Those are the two most commonly used things. But water is much more easily available and cheap. So why don't you just use water and try to measure the viscosity of water using this? Yes? Any idea why you wouldn't use water here?
Water is less viscous.
Yeah, it's less viscous. True. But what will that really cause? This lower viscosity of water compared to glycerin or castor oil. Why is that a problem?
Then the ball will just come down. It wouldn't receive any kind of friction.
Okay, quite good. Actually, yeah, you're right in the sense that, first of all, it's not true that the ball will not feel friction. The ball will feel viscous drag. All bodies moving through fluids feel viscous drag, but it will feel a much smaller viscous drag. And as a result, within the relatively short distance which your liquid column has, the ball will not reach terminal velocity. The ball doesn't start falling with terminal velocity the moment you put it in the fluid, right? It attains terminal velocity. And that won't happen in water at all. Number one. Much more, but even more than that, suppose even if you could manage to have a huge column of water, and so that falling through that, the ball definitely reaches terminal velocity. Even there will be one more problem, one more very important problem, that the terminal velocity will be pretty big. So it will be difficult to measure. The steel ball falling through castor oil or glycerin falls reasonably slowly at terminal velocity. So you can easily measure the velocity. Okay. However, if a steel ball fell through water, it would actually fall very, very fast. Okay. So it would fall so fast that it would be very difficult to measure its speed. But apart from all of that, there is one more very important reason why you should not do this experiment using water. Can anybody tell me what that is? I know I am asking you old stuff, but these are typical questions which people ask in Viva, for example. Even if you had a tall enough water column so that the steel ball reaches terminal velocity, and even if you had a good enough system by which you could measure this large terminal velocity, equating 6 pi eta AV to the weight of the ball minus the buoyancy will not be a good idea. Why? What will go wrong? That's one word which you must have known then, but we have forgotten. What you need for Stokes' law to work is something called streamlined flow or steady flow. That doesn't happen at the very high speeds that a ball would reach inside water. Okay? So the 6 by eta AV formula, that actually will not work. That works only for steady Newtonian steady state flow, not for turbulent flow, which would definitely happen for a ping pong ball flowing through water. Okay? And so for water, we have another experiment which you may or may not have done. I don't think it was part of your syllabus. I don't remember. It's called Poiseuille's experiment, where you essentially take a very, very thin capillary tube and try to drive fluid through it. And the volume of fluid which flows in is related to the pressure head, the pressure difference that you maintain between the two sides. So P2 minus, if you know the pressures that you are applying on the two sides, P2 minus P1 is related to the flow of the water. And from there, you can get the viscosity. And that is one thing which you, in fact, in this case, is the other way around. You would not really be able to do this experiment using glycerin or castor oil, because those are too viscous to actually flow appreciably through a small, narrow capillary tube, whereas water would flow in rather easily. Okay? But in water here, why does viscosity come in? Basically, because what happens is the layers of the fluid just next to the wall of the capillary. Suppose these orange lines are the walls of the capillary, and the layers of the fluid, the blue lines, just next to it, get stuck to the wall, so they are not moving. The next layer moves fast, then moves faster, and so on. So essentially have a velocity gradient, and that's what gives rise to viscosity. Quick question, can anybody tell me why you need this to be a capillary tube, a thin tube, really thin tube and not a thick tube for this experiment to work? Remember, water, has been said a while ago, has very small viscosity. Despite that tiny viscosity of water, this experiment still allows us to measure the viscosity. That means it still actually produces an appreciable force. But why do you need a capillary? Why can't you just take an ordinary straw or any tube that's lying around? Yes? Anybody who remembers the basic formula for viscosity should be able to tell me that. One major hint is water has a very small viscosity. And you want to measure this viscosity, so you want to make sure that even this tiny viscosity is producing appreciable drag force. I hope all of you remember this, that the drag force in viscosity is actually proportional to the velocity gradient, the rate at which velocity changes. That's sort of easy to understand. This force exists because the different layers move with different speeds. So the rate at which speed changes, that actually is an important determining factor in telling you how big this force will be. So if it's a capillary, you have to realize that the thickness is very small, which means within a small distance, the velocity has to change from 0 to quite a lot, the maximum speed in the middle, which means that the velocity gradient is huge, which is why even the tiny viscosity of water produces appreciable effect. Clear? And all this is about ordinary fluid. Now we come to superfluid. A superfluid is a kind of fluid which flows without resistance. There is no viscosity whatsoever, at least to the extent that we can measure, a superfluid has no viscosity. Okay? Now, can anybody tell me how many superfluid materials do we know of, at least superfluid under lab conditions? How many of them are there? Yes?
Helium-4, Helium-3.
Okay. And any else? Anything else? We have two candidates for superfluidity, helium-4 and helium-3. And it turns out that as far as we know, not only as far as we know, almost certainly, under lab conditions, these are the only two things which are superfluid. Nothing else is a superfluid. And they're very different in the sense that helium-4, after all, is an atom whose nucleus is made out of 2 protons and 2 neutrons. Each of these are spin half particles, where two protons and two neutrons have their spin angular momenta adding up together in such a way that the net spin of the nucleus of helium-4 is zero, and hence is a boson. On the other hand, helium-3 is two protons and one neutron, has to be an odd spin half particle. Three fermions cannot give you a spin zero or an integer spin, and the ground state actually spin half. And so the atom here, or the nucleus at least, is fermionic, very different from each other. And well, the helium-4 becomes a superfluid around 2.2 Kelvin, which is very, very low temperature, of course, but still huge compared to the superfluid transition temperature of helium-3, which is of the order of 20 millikelvin, in fact less than that. So basically lower than helium-4's case by a factor of 1,000. And this actually tells you that something very different is happening in helium-3 and helium-4. After all, as we said, we expect this to be a quantum phenomenon at a macroscopic level, somewhat akin to bosons and condensate. We at least expect a large number of particles to go in the same quantum level for superfluidity to occur. Okay? And that is something we can still perhaps understand for bosons, but it would be very difficult to understand from that point of view how helium-3, which is a fermion, can actually undergo something like that. After all, fermions tend to stay away from each other. So a large number of them going into the same state is impossible, right? You usually would expect two fermions to go into the same state. So leave out a macroscopically large number. So the mechanism of superfluidity in helium-3 is quite different from that of superfluidity in helium-4. In fact, in helium-3, what happens is something like pair formation, which happens. You have learned about that in superconductivity, right? Cooper pairs and stuff like that. In helium-3, something akin to that happens. So we will talk about superfluidity in helium-3 only very little in this course. Maybe after we do superconductivity, we can come back and talk about helium-3 superfluidity in some detail. Although I may not have time to do that. But basically, the important thing is helium-3 is really not our major concern right now. Although it is a superfluid at around 20 millikelvin. This is, of course, these are both at 1 atmosphere pressure, under atmospheric pressure. But it's really superfluid for a very, very, very small temperature. Helium-4, on the other hand, is superfluid in a very small temperature, but which is still huge compared to helium-3. And that's what we are going to focus on primarily. But before we go any further, can anybody tell me why is it that we are so sure that these are the only two things that will show superfluidity? Nothing else will show superfluidity, at least under lab conditions. For example, why not hydrogen or oxygen or nitrogen? Why don't you expect them to show superfluidity? Hydrogen, you may say, is fermionic, so let's forget about that. But a hydrogen molecule isn't. Hydrogen molecule is basically like a tightly bound pair of two protons and two electrons. That's bosonic in a sense. If you think of us at some scale, it will behave like a boson. So why don't you expect hydrogen to be a superfluid, whereas helium is? The answer actually is very, very simple. So think of something very simple. Remember, these phenomena happen at very low temperatures. Only at very low temperatures will it be possible for macroscopic number of particles to go into the same quantum state. And these are fluids. That should be big enough hint. Yes?
For hydrogen, there is hydrogen bonding, which will provide it extra stability.
Okay, but that's really not true in the sense that that was a good try. But hydrogen bonding happens in polar molecules where hydrogen is a part, like in water. Okay. Hydrogen bonding doesn't really occur in molecular hydrogen because there is nothing to pull electrons away from the hydrogen there. Although
Van
you are
der
right.
Waals force.
Hmm?
Van der Waals force.
You do have van der Waals force. Good. If that's not hydrogen bonding happens because of polarity of the bond. But van der Waals force, right? So what happens? That's the underlying cause. You're right about the underlying cause, but what is the actual reason why this happens? What is the proximate reason? Let's put it that way. Because of this large van der Waals force, what happens in hydrogen, which does not happen in helium? You're right that helium being inert, chemically inert, being a noble gas, has very, very small van der Waals force. That's true. As opposed to hydrogen. But what is it about this that prevents hydrogen from going into a superfluid state? Think of the temperature. Kind of temperature you need. What would happen to hydrogen at that kind of temperature, around 2.2 Kelvin? Or even around 4 or 5 Kelvin? What state will it be in? When I say state, I mean the simple states of matter, or phases of matter that you've learned about in school. At that kind of temperature, will hydrogen be a solid, a liquid, or a gas?
Solid.
Solid. Well, actually, apart from helium, every other substance would become a solid at that lower temperature. The question of superfluid flow simply doesn't arise. Right? It's no longer a fluid. Helium, in fact, is the only substance which does not solidify even at absolute 0 Kelvin. This is at under 1 atmosphere pressure. You have to exert around 250 bars of pressure on helium in order to solidify it. This is the only material which does not solidify even at absolute 0. And why is that? One reason, of course, is very low van der Waals force. Which makes it very different from hydrogen. But the other reason, there's one more reason. After all, otherwise, the other inert gases would also be possible candidates, if not for superfluidity, at least for freezing at a very, very, very low temperature, like, or not even freezing at 0 Kelvin. What else about helium? Makes it not solidify at 0 Kelvin, even at 0 Kelvin. One thing is true, this is definitely a contributing factor, but that's not the only contributing factor. The van der Waals force is low, but it's not absolutely 0. So you would expect that at some very small temperature, above 0 Kelvin, even helium should freeze into a solid. But it doesn't. And why not? Hint, it happens because of a uniquely quantum phenomenon, which you have all learned about in your quantum mechanics classes. In a solid lattice, do the atoms really stay put in one point? Do they stay fixed? In a solid? Are all the atoms really fixed in the lattice?
No.
They vibrate, right?
Yes,
Is
sir.
that- That's actually the kind of thing which gives rise to heat capacity and other things. But in the case of helium, because the mass is so small, the vibrations even at 0 Kelvin become huge. Why? Because at 0 Kelvin, there's no thermal energy left. The vibrator will be at the lowest ground level. But even a ground level oscillator has some energy. This is a 0 point vibration. An oscillator or an oscillating atom or ion cannot be completely at rest. That would be against Heisenberg's uncertainty principle. Even at its lowest energy state, a vibrator has this half h cross omega amount of energy, which means the atoms would vibrate. That happens for all atoms. But for helium, because of the very, very small mass, even this tiny energy is enough to make it actually vibrate very, very violently. So it's a combination of both the factors, very, very tiny mass and very low van der Waals force, which ensures that helium stays a liquid till 0 Kelvin under atmospheric pressure. Notice that hydrogen actually, H2 is actually lighter in mass than helium, right? So hydrogen also has a huge amount of 0 point vibrations. But for hydrogen, the van der Waals force is substantially larger compared to helium. So it's both the small mass and the low van der Waals force. Both of them are equally responsible. And you need both of these factors to ensure that helium stays a fluid even at the very low temperatures that we're talking about. Nothing else would. Other things would have higher van der Waals forces or at least larger masses, and as a result, much, much smaller 0 point vibrations. Okay? Clear? So this is basically the phenomenon that we are going to try to understand, at least superfluidity in helium-4. Today, as I said, we will essentially look at the history and some experiments which went in roughly historical order, and then we will try to correlate these things that we will learn about superfluid helium. Once we build models of superfluid helium, we will try to sort of understand why these phenomena occur. So before I start talking about the history, any questions about this so far?
Yes, sir. So fluid, I mean, what we are meaning to say, is it a gas type or liquid type?
No, in
Superfluid
this
when we
case,
talk.
superfluid helium is definitely liquid. At temperatures of 2.7 Kelvin, helium becomes a liquid a long temperature before that, actually.
So when we're talking that it flows without resistance, I mean, suppose if I'm keeping this helium-4 in some vessel, then
We will talk
what
about
will happen?
these phenomena we are going to talk about. That's part of the history. Okay. When I talk about the history, we will talk about various things that were discovered. We will talk about exactly these things. What does superfluid flow really mean? Okay. So just hold on till we talk about we will talk about it soon. But you must understand that these fluids are this is a fluid, but it's very different from ordinary fluids. It's a very special kind of fluid where things happen which would never happen with ordinary fluids, because in ordinary fluids, viscosity will always prevent certain phenomena from happening, which are not prevented here. So If you don't have any other questions about what we talked about so far, we will start with the history. But if you have other questions, please go ahead. This one I'm not answering now because I'm going to talk about this too. Okay, if nobody else has a question, let's talk about the history. Even the history is very fascinating and it's a bit complex. But the good thing about it is that various discoveries and phenomena are intertwined with it. So by the time we end with the history, many of the phenomenological things about superfluid flow will also become quite clear, hopefully. Now, the history starts basically in a place called Leiden, uh, which is famous because it had the world's best cryogenic lab in the early 20th century. In fact, it was definitely the leading lab in the world in 1905 or so, and in that decade. And the person who led that lab is somebody whose name I think everybody should know. All of you must have heard his name, Heike Kamerling Owens. Yes?
Yes,
Have you
sir.
heard of in what context have you heard of it? About
Superconductivity.
good superconductivity, the discovery of superconductivity, right? Now, the reason actually why Camerlingos managed to do this was basically because he ran the best lab in the world for low temperature physics at that time. And one thing which he achieved in 1908, long before anybody else, was that he was the first person to liquefy helium. Okay, around 4 Kelvin is the liquefaction point. So that question as to whether superfluid helium is a gas or a liquid is settled by this. Superfluid helium occurs below 2.2 Kelvin. The liquefaction temperature for helium at atmospheric pressure is 4 Kelvin. So around 4 Kelvin. So superfluid helium definitely is a liquid. Okay. Now the big thing was because he could manage to liquefy helium, he could then use that to cool down other things to even lower temperatures, or at least to liquid helium temperatures, and do experiments at very low temperatures, which very, very few people in the world, in fact, nobody else in the world could at right at that moment. Although other labs started catching up. Just hold on. Hello. Who? Oh, Dheeraj, can I call you back a bit later because I'm in a class right now. I will call you back at around 8. Is that okay? 8:30? Okay. Okay. Sorry about that. Um, so, because of this, he managed to do something on the 8th of April, 1911. Okay. Why is this date so famous? Can anybody guess? Why is this April 8th, 1911 so famous? What happened on that day? On that day, what Camerling Owens did was he used his liquid helium to cool mercury. And observe the phenomenon that Mercury suddenly lost all its resistance. So he discovered superconductivity on this. This is the discovery for which he is so well known. And this is the discovery which actually gave him the Nobel Prize on as early as 1913. Within 2 years of the discovery of superconductivity, Caroline Owens got his Nobel Prize for this. But something else also happened on the same day, April 8th of 1911. What Caroline Owens noted in his lab notebook on that day is this. Something strange is happening to helium at around 2 Kelvin. In fact, although he did not realize it at that time, what happened was he was observing superfluid transition of helium. That is, the transition from normal helium liquid to superfluid helium for the very first time. And so this is really not appreciated that much. But funnily enough, these two phenomena, superconductivity and superfluidity, actually were discovered on the very same day, in the very same place by the very same person. However, Camerlingons does not really get much credit for superfluidity. And there's a reason for that. The reason is, first of all, because he was so excited with his discovery of superconductivity, he noted that something strange is happening to helium at around 2 Kelvin, but he did not pursue this for a long time. He was so busy doing experiments with various materials and trying to find out superconductivity in different materials for a long time, for around a decade after this, he did not return to this special feature of superfluidity of helium. Superfluidity was a long way away, but he actually saw the transition on the same day as he saw superconductivity, but he did not pay much attention to that until a long time afterwards. In fact, until more than 10 years later, 1922-23, he came back and took a look at the heat capacity. He came back, meaning he was still always in Leiden. He led the team. He and his team took a look at the heat capacity of liquid helium as it was cooled down below its melting point at 4 Kelvin. And what they found was a curve which essentially looks like this. So at around 2.2 Kelvin, the heat capacity both from lower side of 2.2 Kelvin and from higher side of 2.2 Kelvin blew up. It went off to infinity. At least as far as they could say, they could see the heat capacity was becoming infinitely large at 2.2 Kelvin. This actually is a sure shot sign. This kind of divergence in a physical quantity, especially in thermodynamic quantity, is a sure shot sign of a second order phase transition. So the strange thing that was happening to helium at around 2 Kelvin, which Camerlingons had seen a long time ago, was actually transition to a different phase. Both phases were liquid. So this phase is what Camerlingons called helium-1, which was a normal phase, the phase that you got just after cooling down helium gas to a liquid. And here you had the new phase below 2.2 Kelvin at atmospheric pressure. You had this new phase which he called helium-2. Okay, and this transition got a special name from the shape of this curve. This curve, if you are a bit imaginative, looks like a particular Greek letter. Can you tell me what this curve looks like? You have to use a bit of imagination to see a Greek letter in the shape of this curve. What letter does this look like?
Lambda.
Lambda, exactly. And this is why this particular transition is called the lambda transition. So the fact that liquid helium actually undergoes a phase transition and goes into different phase below 212 Kelvin was discovered by Camerlingons and his co-workers in 1920s, 1922 to 23. In fact, Camerlingons didn't really go on to do much work in superfluidity after that. By the way, I'm calling this superfluidity basically because I know today that helium-2 is a superfluid. But what exactly is this idea that a superfluid is something which can flow without resistance was not explored by the Leiden group at all. They essentially looked at the thermodynamics of the system, saw that there was a phase transition occurring. And in fact, Camerlingons did not really do much in helium-2, even with helium-2 after this, simply because he died in 1926. So he didn't have much time to really explore helium-2. Although, frankly, he had discovered this transition long back in 1911, but he came back and formally found the transition only in 22. So, a little time to talk about this. But of course, the Leiden lab kept on persisting, working on this. So, what they did, during both Camerlingon's lifetime and after his passing, was essentially try to map out the phase diagram for helium, which means so far we have only been talking about transitions at atmospheric pressure, right? Things which happen only at one atmosphere. But as we know that changing pressure will also change transition temperature and stuff like that. Now, one important thing is, if you think of an okay, let's draw an ordinary materials transition curve. Like say water. Water is very, very extraordinary, very different from normal materials in many ways. But in some senses, it's sort of like an ordinary metal. At least compared to superfluid helium, it definitely is ordinary. And there the phase transition curve essentially looks like this. You have one line like this, another line like this, and a third line with joints here. You have seen phase diagram of water. This is the phase diagram of water, or at least the basic phase diagram of at least the simple phases of water. What do these three lines mean? This one, this one, this one. Any idea? You have seen this, right? Phase diagrams of various kinds, especially water, you must have seen.
So solid liquid transition, liquid gas transition.
So which one is which? Okay, in water, this is solid, that's ice. This is vapor, this is liquid. And this line, this line here is actually something we often call the liquid vapor transition line. But frankly, it's really not a transition line, it's a coexistence line. It's for this particular pressure and temperature on this line, on all points on this line, for this pressure and this temperature, liquid and vapor will coexist with each other. Okay. You change the temperature a bit, say from at this point, if you lower the temperature just a bit, it will become liquid. If you increase it just a bit, it will become a vapor. All of it. But just at this pressure and temperature, liquid and vapor can coexist in equilibrium. And this line terminates at a point. What is that point called? The liquid vapor transition line terminates. Does not keep on going forever. What is this point where the liquid vapor line stops? What is that called? All of you must have. And okay, there's another very special point here. This point where the three lines meet. What is that called?
Triple point.
The triple point.
This one is the triple point, right? The point where the three phases, solid, liquid, and gas, coexist. What about this point? What is that called? The line where the liquid vapor coexistence curve, okay, the point where the liquid vapor curve terminates.
Critical point.
That's the critical point, exactly. That's TCPC, the critical temperature, critical pressure. In fact, it's actually perhaps way more important as far as statistical mechanical properties of the material is concerned than the triple point, than other points. This is actually the single most important point perhaps in this whole diagram. But anyway, let's come back to what happens in helium. Helium, in a way, is similar. You do have coexistence curves, but helium, for example, has a liquid vapor coexistence curve which does terminate at a critical point. But notice that it does not meet any solid vapor, solid liquid transition line, simply because, as I said, even at 1 atmosphere, even at rather high pressures, helium does not solidify at all. So there is no solid vapor transition. What you have is another line up here, and the solid is up here. So you need very, very high pressures. Very low temperatures, definitely, but very, very high pressures in order to produce the solid. So helium will not even solidify at all at atmospheric pressure. So there is no connection between these two lines. And here you have, in between these two lines, you have the liquid. So this is basically the difference. And by the way, because this line terminates at a critical point, you cannot really say that, okay, this is big. There's a huge difference between a vapor and a liquid, because you can go around this critical point and go into a liquid without ever undergoing a phase transition. Now that's what's special about helium. That also happens in water. The difference between vapor and liquid is a lot less than between liquid and solid, so to say. You cannot ever go from a liquid to a solid without undergoing a phase transition, undergoing a drastic change in properties somewhere. But you can actually go from a liquid to a vapor without a phase transition. You can just go around the critical point. But apart from these three phases, which would happen in ordinary materials, with the difference that, of course, there is no coexistence for helium between the three phases, something else happens which is very special. There's another phase transition which happens between the two liquid phases. So you have helium-1 on this side and helium-2 on this side. And this is the so-called lambda transition line. At every point on this, there is every value of pressure and temperature shown by this, you have this helium-1 to helium-2 transition. Okay? So this is something which the Leiden lab mapped out in full, the full phase structure of helium. What kind of phase transitions occur, where do they occur, and so on. Okay, before going any further with the next part of the story, let me just tell you one thing. At this point of time, when they mapped out this phase diagram properly, they actually could also figure out what really was happening. Is this something strange that Camerlingons had noted down so many years ago? What really was happening there? What Camerlingons had observed is something like this. If you cool down helium below its liquefaction point and store it in a vessel, it boils, because basically because there would be some amount of vapor on top of it, and the liquid would sort of start boiling until the vapor pressure reaches saturation vapor pressure. It literally boils even at that low temperature. But once temperature reaches below 2.2 Kelvin, the boiling suddenly stops. All of a sudden, liquid helium stopped boiling completely. and there was no further boiling. That was what Cameron had noticed at this strange phenomenon which occurs below 2 Kelvin in liquid helium. Now, what exactly is happening here? Okay, you have all seen boiling, say water boils, right? Now, when water boils, does the entire liquid boil? You've all seen this, right? You've all made tea or whatever. You must have seen water boil, right? So when water boils, does the entire liquid boil at one time, one go? Especially if you have seen the phenomenon before violent boiling starts. That is, when we usually shut down the gas flame. Uh, Before that happens, you have seen what the initial stages of the boiling. You would know the answer to that. What happens when water boils? Does the entire liquid boil or a small region boils?
Small region.
Yeah, small regions start boiling basically because of various imperfections, instabilities, and so on. Some part of the water becomes superheated, much hotter than the rest of the water, and that superheated water becomes vapor, and this vapor rises up to the liquid, and that's what you see as boiling. The superheated vapor, which are formed in pockets of the fluid of water, for example, and which rises up to the liquid water simply because it's lighter. Okay? So that's what happens. In fact, that becomes more and more, well, more and more of that happens. Ultimately, the whole thing begins boiling violently, but essentially small pockets boil. Now, what Kamerlingh once had observed is that just below 2.2 Kelvin, boiling stopped completely in helium. That is, small pockets of helium superheating. For helium, superheating actually means something getting close to 4 Kelvin, not superheating as in boiling water, but the same phenomenon. Small before 2.2 Kelvin, what happened was small pockets of liquid helium became superheated, became vapor, and the vapor rose up to the liquid, and that was boiling. Below 2.2 Kelvin, that thing suddenly stopped. So superheating suddenly stopped. Can anybody guess why superheating would stop? There is one part suddenly becoming much hotter than the rest. Much hotter here, of course, is relative, but still much hotter than the rest. That didn't happen once helium-2 formed. And let me give you a hint. Okay, the basic property that happens here is this. Helium-2 is a much better conductor of heat than helium-1. Much better meaning heat conductivity of helium-2 is around 1,000 times better than the conductivity of helium-1. The conductivity jumps by a factor of 1,000 or more. But why would that stop boiling? You just think of why boiling occurs, as I explained right now. You should be able to tell me the answer. Yes? Remember, boiling happens because parts of the liquid heat much more compared to the other parts. And they form vapor and they rise up. That vapor rises up. So why is this much better heat conductivity of helium-2? Why will that prevent this from happening? Boiling from happening? Yes? Again, there's something which this doesn't require any specialized knowledge. Okay, you do need to know some physics for this, but you need to know only basic physics for this.
So can you repeat the question?
The question is simply this, that what commanding Holmes saw was that once temperature fell below 2.2 Kelvin, which he did not know at that time, but later people found out. He himself and other people in his lab found out helium-2 was forming. Boiling of the liquid stopped immediately. Just below 4 Kelvin, helium forms a liquid, but it boils rather violently. And remember, just like water, when it starts boiling, it actually starts boiling before the entire water reaches 100 Kelvin, 100 degrees Celsius. Right? Because parts of the water superheat. Despite the rest of the water being still at 95, 96, 97 degrees Celsius, parts of the water become much, much hotter than that. It becomes hotter than 100 degrees Celsius, form vapor, and rise up. That's why boiling occurs. Similarly, when you drop below 4 Kelvin, helium liquefies, but keeps on boiling. Suddenly at 2.2 Kelvin, it stops boiling. And the feature which is responsible for this is helium-2, which is now what forms, is actually a much better conductor of heat than helium-1. But why would that stop the boiling? That's the question. Why would this much better heat conductivity of helium-2 stop the boiling of the helium, which is what Camerlinghuis had seen the same day that he had discovered superconductivity? Yes? Again,
Since it is a better heat conductor, it will transfer and dissipate heat much faster.
exactly. And that is why superheating will never occur. Regions becoming hotter than the rest. That would, of course, that could happen in liquid helium, that happens in water, because water is a bad conductor. So it doesn't conduct heat away from the super hot portion. But helium-2 becomes such a wonderfully good heat conductor, even much, much better heat conductor than most metals, for example. Even, not most, even than almost all known metals. It takes away the heat from any region superheats. Of course, superheating keeps on occurring locally. But any region superheats, helium-2 would take the heat away so fast that the thing will not have a chance to boil. So this is basically what the scenario was till in the 1920s, where Camerlinghuis and the Leiden team had made these discoveries. But notice one very important thing. In all of this, superfluid flow has not been mentioned once. We have talked about the phase transition which helium undergoes, which was discovered, the phase diagram was mapped out and everything. But the fact that superfluid flow is what makes helium-2 special. This superfluid helium actually has superflow, flow without viscosity. That was not found out by the Leiden lab at all, at least not at that stage, because they were not even looking at it. They were not looking at those properties at all. Okay. For that story, we will have to come to the 1930s. So it was not until the 1930s that superfluid flow in helium was discovered, which is why the credit for discovery of superfluidity is actually not given to Camerlinghuis or the Leiden group, really. The credit is credit is shared between some people, but the major person among them is Piotr, or later his name became anglicized Peter Kapitsa. He was one of the major players in discovering superfluidity, which is the ability for liquid helium-2 to flow without resistance. But the story here is also rather fascinating. In fact, this story is very fascinating. at this. Okay, but some background before that. In the 1930s, Leiden was no longer the only lab capable of this very low temperature work. After all, other labs had caught up. In fact, apart from Leiden, Oxford had a very good low temperature lab, so had Cambridge and, and Berlin. These were the four leading low temperature labs at that time. There were leading low temperature labs everywhere, other places as well. But these were the ones which were very capable of doing the work at the kind of low temperatures needed, around 4 Kelvin or so. Liquid helium work, basically. Leiden, of course, because Camerlingons had built the lab to do that. But these other labs are also got it. Now, Fyodor Kapitsa was Russian by birth. And at that point of time, USSR did not have any such very low temperature laboratory. They had cryogenic labs, but not this kind. Now, the reason why Kapitsa story, okay, in a way, Kapitsa's story actually occurred perhaps because of something which happened nearly 100 years ago, which is something which actually has been plaguing us for the last few years. Last few years, we have been recovering from a horrible pandemic, right? But you also know that by this time, everybody knows this. 100 years before that, there was also another pandemic. What was that? In the 1920s, there was a very, very severe pandemic. In fact, much more severe than this one. Killed many more people. Also because medical science was not perhaps that good then. What was the pandemic of?
Spanish flu.
Spanish flu, exactly. And the point is, Kapitsa had this misfortune that his entire family was wiped out in Russia because of the Spanish flu. Everybody died. He had nobody left in Russia. So essentially, because he had lost his entire family, what he did was he actually left Russia and went away. Without this misfortune, he might have stuck to Russia and stayed on there. But what he did, he was already a well-trained physicist by that time. He came and joined Cambridge. And at that point of time, the Cambridge lab was directed by an especially famous scientist whom you all know about. Ernest Rutherford was the director of the Cambridge lab at that point. He was, of course, already very famous. Nobel Prizes, and then in chemistry, and then this Rutherford experiment, nuclear theory, nuclear model, all of them. Now, Rutherford saw that Kapitsa is a very, very capable experimental physicist. So what he did was he actually not only hired him, he essentially threw his entire weight in favor of Kapitsa and built him a very, very high-grade lab. In fact, his aim was to build the best low-temperature lab in the world, surpassing the then leader, Leiden. And for that, he actually hired Kapitsa and gave him liberty to do whatever he wanted. And Kapitsa did that. He built definitely the best lab possible at that time. And as a result, one thing which many people do not really know, Kapitsa at that time was paid more than almost any other scientist in the world. His salary was much, much higher. In fact, it was much higher than Rutherford himself. Rutherford was a director, but Kapitsa actually commanded a much higher salary than him. Because Rutherford knew that to keep a person of his talent, he would have to actually spend a huge amount of money. And because Kapitsa's lab became so famous, many people wanted to work with him. In particular, John Allen, who was working in Toronto. He was working in a cryogenic lab in Toronto, Canada, but that cryogenic lab worked in liquid nitrogen. So He was trained, but not trained at that low temperatures. But John Allen actually moved to Cambridge to work with Kapitsa. So his idea was he would join Kapitsa and work under him and learn from him and basically become an expert in very low temperature physics. But something rather funny happened at that point of time. Kapitsa built his lab rather well, so what he did was he took a holiday for a short holiday, around a month or so. Not a month, around 6 months or so. And he visited his birthplace, Soviet Russia. But then something strange happened. It was Stalin's government at the time. And perhaps Stalin himself, or at least somebody close to Stalin, realized that Kapitsa is way too valuable a person, valuable a scientist, to lose to the West. This was before the World Wars, before the Second World War at least. But Kapitsa essentially turned out to become somebody who, and by the way, Russia was an ally of England in the Second World War. But before that, they were really not really in very good terms. In fact, Russia originally allied with Hitler when the war started. And only later, when Hitler turned on Russia and started attacking it, it actually became England's ally. So Stalin definitely did not like the idea that Kapitsa would actually go back to Cambridge and help them. So what he did was he persuaded within quotes, maybe threatened, force, whatever, Kapitsa to join the Russian program. The deal was Kapitsa would be given full powers to do whatever he wanted and be given unlimited amount of money to set up a lab in Moscow, which would actually rival the best, like the Cambridge one, which Kapitsa set up, or Leiden one, and so on. So essentially, politics kept him in USSR. Okay. But so the funny thing was, John Allen, who came to work with Kapitsa, was essentially stranded in Cambridge without a supervisor. He had to learn about the lab himself. He couldn't learn from Kapitsa because Kapitsa was being kept back in Moscow. Now, okay, just as an aside, Rutherford actually made the best of this rather bad situation. He had lost his star physics, but because he had to pay Kapitsa so much, what Rutherford managed to do was, with the same amount of money, he actually hired both John Allen and another person who is very, very famous, although you may not have heard his name so much. Have you heard his name, Rudolf Piles? In fact, if you look up his work, you will find that he worked in almost everything. All parts of theoretical and more theoretical physics, but also some experimental physics. But when Rutherford hired him, he was essentially a nuclear scientist. And among Piles' most well-known contributions, although a notorious one, is that he was the first person to actually realize that you could use a much smaller amount of uranium-235 to build a viable nuclear bomb than what was thought of at that time. Other people thought that it would require way too much uranium to make a bomb feasible. Piles figured out that if you use 235 instead of 238, you can actually build a nuclear bomb with a much smaller amount of material. And in fact, it was Piles and Fritz's work which convinced scientists that the nuclear bomb could at least be built. Piles became an avid anti-nuclear activist in later days, but he was possibly one person who we could blame for actually the nuclear bomb being built. Anyway, that was an aside. Piles has no role to play in our story except the fact that Kapitsa's money went to fund both Allen and Piles at the same time. That was so much that Kapitsa was actually being paid. So now the scenario is Kapitsa is in Moscow. John Allen is in his lab in Cambridge, and what he did was he hired, or he actually invited one of his old colleagues from Toronto, Don Meisner, to come and join him and do the work. And here I might ask you a trick question. Have you heard of Meisner?
Yes, sir. Superconductivity. Meissner effect.
Well, okay, that was why it's a trick question. That's a different Meisner with a different spelling. That's Meissner, a German Meisner who was actually much older than Don Meisner. Okay. So this is a different person, not the Meisner of superconductivity. Okay. So, but now the situation was in 1937-38. So just before the Second World War started, these two people, John Allen and Don Meisner in Toronto, in Cambridge, they were both in Cambridge at the time, of course, and Kapitsa in Moscow, independently discovered superfluid flow. The fact that superfluids can flow through a very narrow pipe, apparently without any resistance. So when you try to push a liquid through a very narrow capillary, you need to have a pressure head. You need to have a pressure difference between the two ends. Why? Because you need the pressure difference essential. So the pressure difference will produce a force which will be needed to overcome the viscous drag which the fluid is feeling. In 37-38, Alan Meisner in Cambridge and independent Kapitsa in Moscow discovered that when liquid helium flows through a narrow capillary, liquid helium below 2.2 Kelvin flows through a narrow capillary, it flows without any pressure head. Okay. So this is one of the features of superfluid flow. What does superfluid flow mean? You don't have to maintain a pressure difference between two ends of the capillary. Despite that, superfluid will flow through the capillary. And in this process, Oxford, which is a traditional rival of Cambridge, was a bit left behind. The Oxford lab, which is also a very good lab, very good low temperature lab. In fact, they were a rival lab to Cambridge's, could not really win the game of discovering superfluidity. So superfluidity discovery, these three people, Kapitsa, Allen and Meisner, these three people are actually credited with discovering superfluidity, the phenomenon. The phase transmission had been, of course, seen earlier, but the phenomenon was discovered by Kapitsa, Allen, and Meisner. And well, in Oxford, somebody called Simon and another person called Rollins was essentially beaten to this by a very small amount by Allen, Meisner, and Kapitsa. In fact, they were also looking at the same phenomena. And in 1939, just before the World War started, they discovered a phenomenon in liquid helium, again, liquid helium below 2.2 Kelvin, which they called supercreep. So what exactly is supercreep? Is this, suppose you have a ordinary liquid in a container. What would happen to the liquid? Would it just be absolutely flat? If it were a large container and you had the liquid in it, will the liquid be absolutely flat throughout the liquid surface? Yes. Any idea? You know this, right? What happens near the edge where the liquid joins the fluid, joins the edge of the container? What happens there? All of you have seen this. If you pour a liquid in a narrow glass and look carefully, you will even be able to observe this. If the liquid gets attracted to the container, if it's not repelled by it, it sort of climbs up a bit, right? The two sides. Have you studied this adhesion of a liquid to the side of a container? A small rise, the angle of contact being acute and so on? Or has the teaching of properties of matter completely stopped nowadays? I don't know. Do you know this? This is just an
Yes, sir.
ordinary phenomenon, right?
Yes.
Now, this rising bit happens because there's an attraction between the liquid molecules and the material of the container. And that makes the thing rise a bit. And the rise stops basically not really because of gravity. The rise stops basically because viscous forces stop the material from moving up. In fact, what Simon and Rollins saw was that below 2.2 Kelvin, what happens if you throw liquid helium in a container is this. The helium creeps out of the container by climbing up the wall and then falling down again. So this is what is this is something which would have happened in a normal liquid, but doesn't because viscosity essentially forces the flow to stop. Here there is nothing to, once the liquid starts climbing up, there is nothing to force it to come down. It essentially goes up and then falls down on the other side. Okay, so this is the supercrete phenomenon which was discovered in Oxford. This is another feature of the fact that superfluidity is fluid materials are very different from ordinary materials. By the way, in 1938, the year before that, the other major lab, Leiden, which had already discovered the entire transition and all that, there, two people, Kaizen and Mackworth, made a very important discovery. What they did was something special. They actually took liquid helium above 2.2 Kelvin and put something inside, a piece of metal inside it, which they made vibrate. Now, when an object vibrates inside a liquid, what happens? What happens when you suppose you took a spring and dipped the bob in a liquid and made it vibrate? What would happen to the oscillation? As opposed to if it was, say, in vacuum.
Reduced oscillations.
Well, reduced oscillations, of course, reduced oscillations is really not correct because that will depend on how much you have pulled. It depends on the initial conditions, right? But when you say reduced oscillations, what you really mean are damped oscillations. Much bigger damping, right? You put something in a liquid and make it go, it's going to be, the motion is going to be damped out much faster than in, say, in vacuum. Okay. So when Chisholm Mackworth tried doing this with helium above, say, they first saw how well a spring-like object vibrates in the ordinary, in vacuum. Then they put it in liquid helium. Of course, they had to be careful. They had to ensure that the material would still be elastic at liquid helium temperatures. Most things would actually become very brittle. But they managed to find such material. And they made essentially a spring vibrate inside liquid helium. Of course, they saw damping. Right? But now, if you reduce the temperature of liquid helium below 2.2 Kelvin, what would you see? What would you expect?
No damping.
Right. That's what they would expect. They saw actually this. Now, of course, that's what you might expect from theory, but in physics, experiment is the supreme thing. Theory ultimately has to obey whatever experiment tells you. And what they saw that below 2.2 Kelvin, a body vibrating in helium, that is in helium-2 now, experiences, well, reduced but non-zero damping. So this was very strange. Superfluid flows through a capillary told you that superfluid can flow through a capillary even without any pressure head, which essentially means, and supercritic essentially says it can climb up walls and go down, shows that there is no viscosity. Yet, when you try to make something vibrate inside the superfluid helium was producing some amount of damping. The damping became smaller as you kept on lowering the temperature. But at least at around 2.2 Kelvin, in fact, around 2.2 Kelvin, there was almost as much damping as in helium-1 as in helium-2. It's only when you reduce the temperature further, damping actually went down. So these two things seem to behave very, very differently. Two very opposite features seem to be at work here. Okay. One set of experiments seem to tell you that there is no viscosity whatsoever. Another set says no, there is some residual viscosity. So this was a big puzzle. Now this puzzle, two people tried to resolve this puzzle at the level of theoretical explanation. And these people are Laszlo Tisza and Fritz London. Once again, one of these two people you must have already heard about. Which one?
London.
Yeah. In fact, you heard about not only one London, you heard about two Londons. Fritz and Heinz London, they were two brothers who actually had given the first phenomenological description of superconductivity using what is called a two-fluid model. Basically, they took the cue from Bose-Einstein condensation, where, remember what we said was, as temperature drops below Tc, you have a condensate, all of this which is in the same level, and also non-condensed atoms, which are in other levels. And at Tc exactly, there is actually very little condensate. But when you go below Tc, N0 by N climbs up to 1 at 0 Kelvin. So Bose-Einstein condensation, once it occurs, when you're at a temperature like this, somewhere here, you actually have both a condensate and a non-condensate together. And London actually tried to use that, and an analogy with that there were two kinds of materials in a superconductor, one which was superconducting and the other which was non-superconducting. And that's actually worked rather well and gave them a very nice phenomenological theory of what superconductivity is like. But Tisza and Fritz London, one of the brothers, did with superfluidity was try to explain these phenomena, viscosity not being absent or seeming to be there in one experiment, not seeming to be there in another experiment. They tried to explain this by a very similar picture. In fact, they tried to essentially say that this is essentially Bose-Einstein condensation which is occurring, and the condensate essentially the superfluid and the non-condensate is not. Now we will see that the next major player in this story, whose story I'm going to say the next part, perhaps one of the best known, or if not the best known, at least one of the best theoretical physicists of all time, Lev Davidovich Landau, was the next major player in this story. And he essentially built upon the two-fluid model in a very big way. At the same time, his first reaction to Tisza and London's work was it's all wrong. because he managed to show very easily that Bose-Einstein condensation, at least the kind of Bose-Einstein condensation which Einstein had worked out in non-interacting bosons, can never be responsible for superfluidity. So that's the story that we are going to start on the next day. I've already run out of time today, so if you have any questions about this, please ask. But we are otherwise going to hold this up for the day. We have essentially introduced superfluid phenomena now, but we will see more of the basic phenomena in the next lecture, as well as essentially start talking about Landau's major theory, which essentially is our first major theoretical thing in this whole picture. So, any questions about what I have said so far? Okay, if not, what I'm going to do is we will call it a day today. Next week, also Thursday, maybe a bit earlier, maybe 6:30 is okay with all of you? That means, of course, if anybody has a problem with 6:30 at the time, then tell me.
So it actually takes time to come home from college. I come
Okay.
around 6.
Okay, so 7 is fine. I was thinking that
So,
you might want to get it a bit earlier, but if 7 is fine with me. Okay, next Thursday at 7.
Okay, sir.
Okay, bye for the day. And hopefully it didn't drop, or my voice wasn't lost anywhere in the middle, right, today. Did it?
স্যার কোনো রেফারেন্স বই এটার জন্য
রেফারেন্স বই এটা এই হিস্ট্রি পোর্শনের রেফারেন্স বই করার দরকার নেই, কিন্তু ওকে, রেফারেন্স বই এটা এই পোর্শনটার জন্য অ্যানেটের একটা বই আছে, আই এম নট শিওর whether I'm writing the spelling right, maybe CTE, superfluidity and superconductivity. You should be able to find this. Most of what I'm going to talk about will be from that, and superconductivity also part of it will be from that, part of it will be from Tinker. Tinker is a pretty well-known book. I'm pretty sure all of you have heard of it. So these are the two books we are going to follow most. অ্যানেট হচ্ছে ওই অক্সফোর্ডের যে সিরিজটা, গ্রাজুয়েট সিরিজ, যে পাতলা পাতলা যে বইগুলো আছে সেগুলোর মধ্যে একটা। I'm not very sure whether I'm spelling this right. Could be ANNETTE or something. But the name is Superfluidity and Superconductivity. History mostly you will find from the net or many other sources. But I'm pretty sure you don't really need to know. The reason why I brought in the history is that the history also gives us a nice way of introducing the phenomena. And it's also pretty fascinating. In the next part with Landau will become even more fascinating. It's like it's essentially like a thriller, the part with Landau at least. There's politics, there's intrigue, there's lots of other things in there. But we will try to keep that short and talk about the actual contribution which Landau made after that. Okay. So bye for today.